Thanks for the great introduction. I'm focused on AI and data science. That's what the R&D Center in New Delhi is focused on. And on behalf of that team, I'm very happy to be here and show you what work we've been doing. So this is going to be a pretty packed session. We've got a lot of content for you. Please let me know if I'm speaking too fast or I need to slow down, or maybe you can, if you want me to go faster, you can do like this. And you want me to go slower, maybe you can give another sign. So we are going to start off by talking about, just an introduction of what is AI, what is machine learning, what is deep learning, where does it all fit in, and how is it related to data science. Then we'll look at machine learning, and I'll show you how it is different from deep learning, where Arcgis comes in, what machine learning tools are there, how can you use it. But not everyone uses tools. In particular, data scientists right now, they are using Python to find the answers from their data, and they're using this medium of a notebook. So we'll look at what are these notebooks and how they have been integrated in Arcgis, and how you can use the Python API to do spatial data science. Then we'll go and talk in detail about deep learning and how you can use the tools in Arcgis and the APIs to train your own model, how you can adopt deep learning in your workflows. And finally, we'll end with some resources and getting started. So when we talk about AI, machine learning, and deep learning, even for a person like me who's been in this industry for a little while now, when I go to a computer vision conference, which I was in like 2 weeks ago, there's so many terms being thrown at you, and it can get overwhelming. I'd like to parse it down to 3 important concepts. At the top is artificial intelligence, which is the ability for a machine to exhibit what you typically associate with a human, some sort of intelligence that typically we humans have. There are many ways of doing AI. One of the techniques that is based on data-driven algorithms. By looking at a lot of examples of data and what the outcome was, if a machine is able to do that, we call that machine learning. There are other types of AI techniques like reinforcement learning, which involves a reward mechanism. But machine learning is typically those things that are related to data-driven algorithms. And deep learning is one type of machine learning which is inspired by and loosely resembles the human brain. There are several layers of these neurons connected in a deep neural network that can then start behaving like a brain and start giving answers. And data science is not a subset of either of these. It sits along with them. It's about getting insights out of data, typically using a medium of notebooks or Python, but really you could also use tools. And it includes visualization techniques, analysis, and that need not be, you might not always be using machine learning and deep learning to do that. So with that context, you might be wondering, okay, that's great, but where does Arcgis fit in? Well, Arcgis has been a data science platform. It has enabled spatial data science, and now it also, with the introduction of Arcgis notebooks and the improvements in the Python API, the relatively newer Python API and ArcPy, you can do data science within the platform with Arcgis notebooks. It integrates machine learning and deep learning. It also lets you interoperate with external machine learning and deep learning frameworks. So it has a lot of these new tools that have come in. We've got tools related to clustering, classification, and prediction. We're going to see that. The notebook integration allows you to leverage what's there in the open Python ecosystem, bring that in, combine that with what is in Arcgis, then you can start answering questions. So with that, now let's look at machine learning, the broader term, and what I mean by it being data-driven. And I'm going to give you, or start off with an example, and introduce some terms. So the problem that we are going to try to solve is of predicting churn it's a telecom term. So all of us have mobile phones, and we typically use one mobile provider for making calls. And for any mobile company, a network provider, for each person, if they experience some number of call drops, if they call in with some number of complaints, and they've subscribed to this package, there's an outcome. The outcome is whether they stayed with the network or they left and joined a competitor network. So for these companies, there are these features which could be responsible for predicting the outcome, which is whether they got churned or not. So using these input features and the output labels, and given a lot of data of how many people stayed with the network, we can now use this data and train a machine learning model to find a pattern to this data. And this could be techniques like, there might be a linear relationship. There are some examples shown here. There could be a polynomial relationship for which you'd use another, linear regression or linear regression with polynomials. You could use random forests. You could use support vector machines. You might have heard of terms like these. These are machine learning models. And you fit the model, the data to the model. That gives you a trained model. And with that model, for a new subscriber or someone who hasn't churned, we can see, okay, he's experienced so many call drops. He's with this plan. Is it likely that this person is going to leave our network? And if it is, then they might want to give you some offers to stay with the networks, or they might want to fix the problems in your area. So with that, I hope you know what these important concepts are, which are input features and the output labels, and how you fit the model to the data. And here are some examples of how it could be applied to GIS and solve some other problems. So if there are, let's take the example for road accidents. So they happen on a road. So we need to know what the road segment type is. The accidents are probably related to their spatial location. Is it near an intersection? If it is, then the distance to the intersection could be another factor. The time of the day, the month of the year, there could be seasonal variations. There could be the rush hour traffic that's important. There could be proximity to the billboards. And all of these are input features using which you can train a machine learning model to predict whether, given these set of features, how likely is an accident going to occur. So with that context, now let's look at machine learning specific to ArcGIS. ArcGIS has included machine learning tools for over a decade now, and that includes tools for classification, for clustering, and prediction. So let's look at a few examples. There's prediction, in which we've got tools like the empirical Bayesian kriging. There are tools to find hotspots. There's this example here that's used for climate downscaling. There are some spatial machine learning tools like geographically weighted regression that are also there. Then there's classification, which is used for land cover classification. In this example, you might have heard of maximum likelihood or random forest support vector machines. And these are machine learning techniques to solve these problems. And then there's clustering. So given a bunch of points, how can you create meaningful clusters out of them and try to find some insight from them? So let's look at one example, which is to predict where dengue fever is likely to occur given known locations of dengue fever. So here we are looking at Kenya, and the points marked in red are where there have been incidents of dengue fever. Now, there have been some studies. There's a paper from which a data scientist can see, okay, what are the factors that could be responsible for dengue fever? Well, the study said that the elevation and land cover is important because that's probably going to tell where the mosquitoes are there, which is, who actually spread that disease. The population density is an important input factor. The temperature is important. So given all of these important factors, you can bring in those data sets in ArcGIS. Here we have brought in the temperature. This is showing the distance to the water bodies. So near the water, the river, it's less distance. This is the land cover. So you can get in all of these input data sets. This is showing proximity to where the hotels are, where people come from different places and they might be spreading the disease. And this one is another one, which is where the population clusters are. So given all of this data, this is showing, I think, I'm not sure about this. This is probably the population clusters. So given all of this data, how can we predict where dengue fever is likely to occur? Well, we know where it did occur, but we do not know where it did not occur. And to train a machine learning model, you need to give it examples of both. So the way we found places where dengue fever does not occur is also using spatial techniques. And for that, what we did is for all the pixels in this country, based on a grid that we've created, we found how similar are they to the points given all of those factors where dengue fever did occur. So we used the Find Similar Points tool to get this raster. And then, this is a problem where the points that are most similar, if we were to uniformly pick from them, we'll get an unbalanced data set. So a lot of, if we were to uniformly pick from them, a lot of these black points, which represent where it did not occur, would be in similar locations, but we want to spread it out. We want to create a balanced data set. And for that, we use another tool to balance these out, and you can see these are spatially balanced points, which can now be used to train our model. So then we can use the random forest tool that is built into ArcGIS, giving in all the exploratory variables, where it occurred, where it didn't occur, and the bioclimatic factors, and we train a model. Once we train the model, one of the advantages of this model is it also gives you the importance of the different features. So in this case, we know that the distance to hotels was an important factor for spread of dengue fever in Kenya. So you get these insights. And then you can run this tool in prediction mode, and this is the points where it's predicted. So we can see a lot of places where it actually occurred fall in the pink, the orange areas. And there are other areas which are susceptible to dengue fever. So that's where we can allocate resources to try to fight this disease. So that was an example of machine learning. And I'd like to use this slide to explain how machine learning is slightly different and not just a subset of deep learning. What I mean here is the traditional machine learning, it was the analyst who found out what the most important factors were. So the distance to the hotels, the precipitation, the land cover. As an analyst, you need to know what those important features are. And what the machine is doing is given those input features, it's just fitting them to the results. It's not really exhibiting that much of an intelligence. And where it's different with deep learning is that the computer figures out what those important factors are as well. So for example, let's say we give a picture of a car and the computer has to tell what object it is. We give it all the pixels, and it first needs to find that, okay, if it's going to be a car, there better be 2 headlights, there better be something round that looks like wheels. And based on those intermediate features that it decides to compute, the later layers of the neural network will use those features to come up with the outcome. So deep learning is an end-to-end training of the model in which it figures out what the most important features are as well. So ArcGIS includes machine learning tools and deep learning tools, and it also is an open platform. So you can integrate with external frameworks like you might have heard of TensorFlow, of PyTorch, and you can integrate it with ArcGIS, get your the input data to those platforms, get the results back into ArcGIS. So, I showed you using ArcGIS Pro as a tool for data science, but not everyone uses tools. There's this, this new breed of data scientists, like Ewan was saying in the morning. Everyone wants to call themselves a data scientist. And when you go out in the data science world, you go to Kaggle, where these competitions are run, you find that many of them are using notebooks. So we've integrated notebooks in ArcGIS, and they enable spatial data science. Before I talk about it, just to know how much in depth I want to, or at what speed I should go about this, I want to know from a show of hands, how many of you know about notebooks? Okay, so about 40%. So what these notebooks are a browser-based tool where you can write text and describe what your analysis is about. You can also put in code, Python code, to do the steps of your analysis, and your results are also shown in the notebook. It's a browser-based scripting environment and uses Python. And we look at that, it'll become a lot clearer. But why Python? Python has become the lingua franca, or the common language to talk to these data science libraries. It's the most popular library for data science. And a couple years ago, you could say that R is neck to neck with it. But more recently, Python has gained a lot of traction. You get a lot of productivity out of it. It's very easy to understand. It's very readable. It's a great glue language that can let you call C and C++ code, or even Fortran code. And whether you're doing it, some initial prototyping, in which you typically might have used R, when you go to production, you don't need to switch the language. Python scales very well from small projects to large projects. There's a great set of data science libraries in Python, including pandas, scikit-learn for machine learning, TensorFlow and PyTorch for deep learning, special geospatial libraries as well, GDAL, Shapely, PyShape, PySal. So there's a lot of community as well. So these are the reasons why Python is really the language of choice for data scientists. So what we did was that we took Jupyter Notebook, which is an open source software that creates these notebooks. And it's a browser-based tool, and we've integrated it tightly with ArcGIS. So it really is the intersection of ArcGIS and open data science. So from the ArcGIS side, you're getting the rich set of capabilities, the geoprocessing tools through ArcPy, the spatial analysis, the big data, and the raster analytics tools from Arcgis Api for Python, and the analytics of the platform. And you are marrying it with the rich set of data science libraries in the open Python ecosystem using this medium of notebooks. So how is ArcGIS notebooks different from traditional Jupyter notebooks? Well, like I said, it's tightly integrated with the WebGIS. I'll show you an example of that. We've also integrated the data and the analysis tools with it. We've given you a gallery of notebooks to start your analysis with. And the notebooks that you create are items, so you can share your work with others. It enables collaborative data science. Another new capability is that you can use ArcPy in the notebook environment that does not need ArcGIS Pro to be installed on the notebook server. So that's another way to interact with the hundreds of geoprocessing tools through the medium of the notebook instead of going through ArcPy and clicking buttons. There are over 175 open source libraries that we include, and we also let you configure them as well. And if you were to do it yourself, you might have realized that it's not easy because the dependencies of one library conflict with another, so there's a lot of value addition there as well. So let's look at the notebook interface. I'm going to show you a quick demo of what it looks like. So I'm going to my portal, which is ArcGIS Enterprise, and since I'm signed in as a data scientist, I have the privilege to now open a notebook in one click. So just like people could create a map, now data scientists can create a notebook. And behind the scenes, it's spinning up a Docker container, which isolates my work from others and also protects the resource. Don't end up taking all the memory, all the disk space. It's like a container just for me that's been created. And this is a notebook interface. As you can see, it has these cells where you can have narrative, which is in markdown format here. And there are these cells which can contain code. So I can easily go ahead and change this to describe what I'm doing. So let's say I'm in Israel, so I can do that. I could search for some images. So here I was searching for sinkholes near the Dead Sea. I can grab its URL. I can embed that using Markdown. And this is to describe what my analysis is about. And when I run that cell, I get these. I can delete a cell like this. And here's a cell which has some Python code. And that's where we are bringing in ArcGIS API for Python and connecting to our home GIS. Now, since my home GIS is this portal to which I'm logged in, it's also picked up my identity. So it knows exactly who I am and what privileges I have. So if I were an administrator and I were to, I did some administrative tasks like clean up users' folders, and I shared my notebook with you, and you ran it, and it picked my credentials, you would have ended up deleting other people's stuff. But since it's using my credentials and my privileges, it can only do the things that I'm allowed to do as an administrator. You cannot accidentally cause harm to others as doing that. So another thing we've done is we've integrated it with your content. So your organization may have some data that you want to bring in. In this case, we also have data from the Living Atlas that you can search and get in. Here's a nice web scene which is a bridge from Rotterdam. So you can use ArcGIS API for Python and get the web scene class and create a web scene out of this item. And now in our notebook, we have a live 3D map embedded, and it's interactive. So I can use it to visualize the data sets and the results of my analysis. Now I could also create maps. So if I were to create a map of Israel, or let's say Tel Aviv, I just give it a location. I'm assigning that to a variable that I can then query. So it's now created a map of Tel Aviv, and here it is. Now, I could search ArcGIS Online for some content. So let's say I search for bike lanes in Tel Aviv, and we get some results from there. And these are some data sets that I can use for my analysis. So we have this bike route map. We can get information about this. And if I like that item, I can just click the plus button, and it embeds the code inside my notebook. Now, it called it an item as well, but my previous variable was also called an item here. So I can give it a sensible name, in this case, a bike routes name, and I can add these to my map as well. So I can just say map.addLayer and give this bike routes variable, in which case my map has been updated with the bike routes. So that was a quick tour of just getting started, showing you how interactive this environment is, where you can do your data science. And the analysis tools in ArcGIS was also integrated in the notebook interface. So let's say I wanted to call some tools. The standard analysis tools are there. I can just click on the plus button, and it embeds the code for that tool. I can query the help to see what kind of parameters it's taking, pass those in, and do the analysis right here. And not just the standard analysis tool, the big data analysis tools and the raster analysis tools are available as well. So let's switch over to the slides and do a quick recap of what we saw. We saw how Jupyter Notebook has been tightly integrated with ArcGIS. You can get the tools and the data sets, and it automatically gets in the snippets. You get access to the content within your organization, the Living Atlas, the ArcGIS Online. There's also a place where you can upload your own data sets and work with them. So you get your own space to work with. You can create and run scripts with ArcPy. I did not show you that, but I'll show you another example later, which is using ArcPy there. This is the private workspace that I was talking about. You get that, where you can create your Scratch databases and upload files and work on them in your web-hosted notebooks environment. And this includes a lot of Python libraries and packages out of the box. Now, notebooks are saved as items. So if once I've completed my analysis, I can save this notebook, and it would have saved it as an item. I can go to information, give it a nice name, and this is now an item in my WebGIS that I can share with others. So to do that, I just click the share button and decide who to share it with. So I could share it with everyone, or with my organization or particular groups. Then you also can see what a notebook contains. We'll see an example of that without needing to run that code, and you get that secure identity-based access that I showed you. In addition to that, we give you a gallery of starter notebooks that show different kinds of analysis that you could base your work on. So let's look at that. So I'm going back to my ArcGIS Online, ArcGIS Enterprise Notebook Server, refreshing the page. And here it has a link to the gallery of sample notebooks. Let's give it a moment to load up. And we see that we've got a lot of notebooks that you can start your analysis off. So there's this notebook that actually uses ArcPy and ArcGIS API for Python to do a clustering analysis. This is what the notebook item is. I can preview it right here, or I could open it for editing and change the data or the analysis to as I see fit. So this notebook is showing a preview of what it does. It's basically using ArcPy to show where the restaurants are, the popular restaurants are. Talks about the workflow that it goes through, and that's where you can use the rich metadata cells, the markdown cells, to describe what you're doing. And here, it's bringing in a lot of libraries, Bouquet for charting, it's bringing ArcGIS API for Python, and it's bringing ArcPy. So it's a very detailed analysis that starts with getting the restaurants and then clustering them using the new clustering tools like dbScan. And it tells about how you can find the most important zones that should be prioritized for creating a new restaurant. And this is using ArcPy and ArcGIS API for Python and some the spatial statistics tools, the find hotspots tools to do that. We also have notebooks that use, this one is finding the locations of where to create a new health clinic where people don't have access to that, using the location allocation tools. This one is using raster analysis, and we'll look at that a little later. So there's a lot of notebooks. Here is one that's using deep learning to detect swimming pools in satellite imagery. So examples of that are there as well. Let's keep going. In addition to the data science notebooks, we also give you starter notebooks for managing your GIS content, and if you're an administrator, to manage your organization. So I am not going to spend more time on it because this is really a data science session. So we went through this sample notebook, and now we can talk about how do you actually, what kind of Python code do you use in that notebook? So how many of you know about ArcPy? Okay, a lot of you. How many know about Arcgis API for Python? Okay, a lot fewer number of you. And really what, if you use ArcPy, it's the Python API to your desktop GIS. So everything happens on your computer, and you have over 1,200 geoprocessing tools that you can use. Arcgis API for Python is the equivalent for the web GIS. So all the capabilities in your web GIS, be it ArcGIS Online or ArcGIS Enterprise, you can get in through this API. And it includes this. On the right is a module diagram of what the different modules are. They let you work with feature data, raster data, network data, let you call geoprocessing services hosted as tools, and do a lot of these things. So we'll look a little closely at what kind of data science capabilities are there in ArcGIS, and how can you use them through Python through this API. So we'll start with spatial analysis tools, and you might have seen these tools in the ArcMap. There are tools to summarize your data, to find locations, and so on. We'll see a few examples of that. So here, we want to basically just aggregate points. So there are on these, the black dots here showing relief centers, and we want to know the number of people in each relief center added up for this administrative area. So you can do aggregation like this. Now, sometimes the problem that you're trying to solve, you only have limited data, but you can solve that problem better if you had more data. And ArcGIS includes the Geo Enrichment capability, and what that lets you do is get demographic data and business data about known locations. So here I've taken a layer of crime and added the number of people with the associate degree, the average household size, average household income, the number of people with bachelor's degree, and adding these kind of variables as input features to your, when training a model could make a big difference. So this is another important tool that you have, another important capability. Then there's the ability to do proximity analysis, finding routes. That's available through this API. Then there's simple things like buffering and doing overlay analysis. You can do that as well. Now there's tools for spatial analysis like interpolating points. So in this example, it's taken rainfall from a number of weather stations and interpolated them, because rainfall is a continuous phenomenon. It's not as if it only rained at the weather stations. You want to create a surface of what the rainfall might have been given it was recorded at these levels at these weather stations. Then you can do things like geocoding. So you might just have an address, but you don't know where it lies on a map. So the way to do that is you just take that address in a variable, pass that into the geocode method, and boom, it's been geocoded. You can now add it to a map. It could be more sophisticated, so you can have multi-field addresses which are supported as well. It lets you do things like point of interest geocoding. So finding all the Starbucks coffee shops in a neighborhood. You could do things like that. So all of this information is coming from the Arcgis online geocoding service, and that's how you get it very easily without needing to set up your own infrastructure. Batch geocoding, where you've got a bunch of addresses, is similar. Instead of passing one address, you give a list of addresses. There are more capabilities in the API that let you geocode hundreds of addresses using batch geocoding, thousands or tens of thousands of addresses, using some tools that are in the platform. And if you've got big data and millions of addresses to geocode, you can use Geo Analytics Server to do that as well. Reverse geocoding, which is taking a latitude and longitude and finding the nearest address to that. So that's similar. You can use that as well. Then here are some examples of what you can do with the network analysis capabilities in the platform. So you want to find simple routing. You can do that. Routing for a fleet of vehicles, you can do that. And some of our biggest customers are courier companies, and they use sophisticated routing algorithms like the vehicle routing problem. You can do those as well. You can do location allocation to find where to create hospitals to serve a number of people in that area. So a lot of sophisticated analysis capabilities are in the platform that you can call using Python code. This is showing 5, 10, and 15 minutes of drive time from a particular fire station. Which areas could we service in 15 minutes? Then there's Geo Enrichment. We saw that briefly when I was looking at the spatial analysis tools in Arcgis Online. But there's more that you can do. Let's say you don't have geographic features, but you just have street addresses, or you have geometries like points, lines, and polygons. You can enrich them similarly and add demographic variables to your analysis and without having them as feature layers. This is what this module lets you do. It also lets you, in the bottom right, we are seeing how we were able to get the age statistics of people lying within a fire perimeter and draw their age pyramid. So what are the distribution of people who were affected? You can also create reports. Very important, when you're creating locations for where you want to create a new business. Then it's about big data analysis, which we call Geo Analytics. And here you can use similar set of tools that you did with the standard analysis tools, with the exception that these tools also do spatiotemporal, so time-based analysis in addition to just the space or location-based analysis. And they use distributed computing to split up this task on a cluster of machine, because on one machine, there's so much data that you cannot really process it in a timely manner. So here's an instance of the kind of analysis I did, where I obtained police incident reports for 8 years, and they were in the form of CSV files. Now with Geo Analytics, you can take all of those CSV files and dump them in a folder that you can then attach to your data store, the Arcgis Enterprise. You can attach a folder or a file share with such files. Once you do that, those data sets become available as items in your WebGIS, and these items have layers that you can use for your analysis. So here, what I'm doing is, really I'm calling the find hotspots of the different types of crimes. Where are the statistically significant clusters of crime? What's interesting is that instead of doing it for each crime category and for 8 years of data, which would mean repeating that same analysis like 60 times, I can just wrap it in a couple of for loops and automate this process. And this saves these results in feature layers given here, the output name parameter. Once I've created them, then I can really start answering questions about where are the hotspots of burglaries, like on the left, and where are the hotspots of auto thefts. And as you can see, each crime has a different spatial distribution. But when you look at the same crime for multiple years. Here we are looking at auto thefts for 3 years. We see that there's a striking similarity in these hotspots for each year. And you can use this insight to then start allocating resources and fight that specific type of crime. So that was big data analysis with feature data, with vector and tabular data. You can do similar analysis with raster data and imagery layers. And we give you over 140 such tools, including math operators, data management and conversion functions, interpolation functions, functions like NDVI that use band arithmetic, hydrology tools. And if there's something specific that we left out, you can still create your own custom Python raster functions to do that kind of raster analysis, and you can create these raster function chains to do your processing. That's best seen through a demo, so let's look at that. And this is an analysis of the Thomas Fire of 2017. Now, another data set that's available in ArcGIS online is the Landsat data. And as you know, it's multispectral. Here we are only looking at the natural color, which shows there's a lot of smoke and haze. But we can specify a particular band combination and extract those bands that enable us to see the fire burn scar and even some active fires in the top left region. It can see through that smoke and haze. And for comparison, here's the same area from from before the fires. Now, once you've done that visual assessment, you can also do quantitative assessment. So here, I'm finding the difference in the normalized burn ratio using some remote sensing techniques, band arithmetic, map algebra. And with that, I can find the area consumed by the fire and get its spatial distribution by severity. So we've taken those results, added them to a map, and finally, I'm enriching the number of people within the fire perimeter, getting that demographic information using Geo Enrichment, and we'll be creating an age pyramid in the next step. So of the number of people who were affected and their spatial distribution. So there are a lot of applications of imagery and raster analysis. Here are a few of them. You might have seen them in different demos. Now, another new module that we've added to the Python API is the ArcGIS Learn module. And that's for deep learning. How many of you know about or have heard about scikit-learn? Okay, a few of you. And that's, for those of you who haven't learned or know about it, it is a very popular library for machine learning, and it's very easy to use. And we got inspired by that, and we've created a similar library for deep learning workflows that enables not just expert data scientists, but analysts and those who know a little bit of Python to train very good computer vision models that work on imagery and work very closely with ArcGIS. So when talking about deep learning, ArcGIS has end-to-end support for the complete workflow. It starts with getting your imagery, maybe creating mosaic data sets, or getting a layer, a raster layer. Then you create training data. So to train your deep learning model, you have to give it some examples of this is what you need to look for. Once you've created that training data, we've got tools that let you export that data, and then you can train your models. Once you've trained the model, it becomes a package. You can use that to find these kinds of objects or solve that problem. And you can deploy these models to production. You can use image server to scale it out and do it on a whole country if you wanted to, and you can take action. So this step of training these models before ArcGIS Learn used to be a little complicated. you need it to be an expert data scientist. You need to install external libraries like TensorFlow or CNTK or PyTorch, and it used to be hundreds of lines of code. And you can still do that, but in addition, what we've done is we've simplified this process, and in just a few lines of code, you can train different kinds of deep learning models. In 3 to 5 lines of code, and with no installation if you're using Arcgis notebooks, all those libraries and the dependencies are bundled right in there. And it isn't just about training these models, it's also about exporting your training data. We've got a wide variety of models to train and use, and I'm going to tell you more about it. It's not going to look so complicated. And there are libraries, APIs to manage these models and use them to do the inferencing. And these are the different kinds of things that you can do with Arcgis Learn today. You could find damaged structures, track building footprints, land cover classification. So I'm going to show you a few of these examples. There are examples to find roads in imagery, find oil paths, which is an object detection, and we'll go through some of them. So before I do that, I want to walk you through the steps involved in training and using a deep learning model. And it's really not that complicated. We've given you tools along the way that make your job really easy. So you first start with your imagery, and let's say we are trying to train a model to find the palm trees in this imagery. We first need some training samples to describe to the model what those palm trees look like. Once we have that imagery and those locations of those palm trees, we export this data in a format that's suitable to train a model. These models need, they work on small, tiny, but expensive GPUs, which only have a limited amount of memory, and they can only look at small image chips at a time. So we have to chip it out into small images. Once you have those training samples, we allow you to train your model using notebooks, using Arcgis Learn module. You could also train it externally using other frameworks. Then you can package it up as a deep learning package, which can be used to either detect objects or classify pixels or now even classify features using both ArcGIS Pro on your laptop or desktop, or you can do it for a large area using ArcGIS Enterprise and Image Server. So let's break this down and start with collecting your training samples, for which in ArcGIS we've got the training samples manager that you've been, it's been there for a long time. You can use to quickly collect these samples and save them to a feature layer. Then there's this tool to export the training data. Each image, this is what the training data looks like. These are small image chips using which the model is going to learn. And we support a number of formats depending on the type of model that you're going to train. Then the step to train your model comes, where you could either use Arcgis Learn module in the Python API and do it in a short amount of code, or you could use external deep learning frameworks. If you already have data scientists or you have that expertise, you can still use external frameworks and create a deep learning package which can then be used to perform inferencing. So we've got tools for that too. You can use it to classify pixels, which could be used for land cover classification. We support GPUs for inferencing. And you can do it on Pro or distributed raster analysis. And similarly, there's a detect objects tool as well. So this is the complete workflow, and starting from the imagery to labeling it, the data preparation, training the model, detecting objects, doing downstream analysis, and then taking the results to the field, Arcgis has complete support for the end-to-end workflow. So now let's look at the actual thing that I was most excited about, which is to tell you how to really do deep learning, what it means, and how to do that with imagery. So the reason why imagery is a sweet spot for deep learning right now is that over the past few years, computer vision, the field of AI related to making computers see, has become so good that it's probably better than humans at some tasks, like classifying images. So here are the results of a competition that's very popular, which, where a computer is required to identify millions of images into 1,000 classes. And till 2012, it was machine learning. Deep learning wasn't at that stage yet. And they used to have a 20 to 25% error rate. And that's the kind of error rate you could expect if you're still using machine learning techniques for computer vision tasks or imagery tasks. Then over the years, the accuracy became so good that in about 2015, according to some researchers, it became better than humans, and it became so good that we can no longer judge computers at it. And for that reason, they had to stop that competition. So what are those computer vision tasks and where computers are really good, and how do we bring them into GIS? And that's where I want to show that in this slide. One of the tasks is semantic segmentation. And for us in the GIS or remote sensing world, we've been calling it pixel classification. So in the image on the left, basically wherever there was a cat, all those pixels belong to the cat class, the green pixels belong to the ground class, and the blue ones belong to the sky class. Well, that's exactly what we do when we do land cover classification. We want to know which pixels representing the ground represent buildings, which ones represent the grass, which ones are water. So this is, has applications in land cover classification, has applications in finding building footprints, extracting roads. And we've got two types of models in ArcGIS Learn to do this. So let me show you an example of that. So in the morning, we saw this demo. How many of you saw this demo? Right? Most of you. Where we were able to use deep learning to find which homes after a devastating fire are damaged, shown in red here, and which ones are still unaffected by the fire. And we were able to do this because we had the post-fire imagery, and we had this layer of building footprints. So we could go to each building footprint, find the area around it, and make a determination, is it damaged or not? That's what a simple cat versus dog classifier does, for example. Now, there could be some areas, which did happen in our case, where the building footprints were missing, or there could be newer developments, like here. So this is a newer development where we do not have that data for the building footprints. Could we use deep learning to find these building footprints? Well, what we did was we took the existing building footprints to train a model. Let's look at the building footprints. We've got like 11,000 buildings in this area. We trained a deep learning model. We used the existing building footprints as training data. We exported that using the tool in ArcGIS Pro. And here are these image chips in which the existing building footprints are showing up in the pink color here. And this serves as training data to train our model. And the type of model that we want to train is a UNet classifier. Basically, it's a pixel classification model. For each pixel, it's going to tell whether it's building or no building, right? We find a learning rate by looking at this graph. And essentially, what it's doing is, a learning rate is probably the most important parameter for training your model. So imagine a child who has been born and he's looking at the world and trying to understand it. If you give it a small learning rate, if the child learns at a slow rate, it's going to take him a long time to learn. But if he's very quick to grasp onto things, he might be, for each example that he sees, he might be heading off in a wrong direction because there are some, there has to be generalizability. So it's similar with these models, and you need to give it the right learning rate. And we have these tools like the learning rate finder that now actually return the exact learning rate that you should use. And I'll explain to you how to pick that. Here's the code to fit the data to the model. And here are the results once I've fit the data. You can see on the left is the training data that was used. On the right are some predictions. So the model has found that these are buildings. It even found the one in the top right corner which we forgot to label. So the model now knows how to find these buildings. This is another example here where we missed labeling this, but the model knows, okay, that looks like a building. Once you have that, you can save it out as a Esri model definition. You can use Pro to do the inferencing. In this case, I actually used image server, and all that needs is the imagery and the extent where we want to process it. And we can use the same tool using the Python API, and this is using distributed raster analysis, a cluster of 4 machines with 4 GPUs to do the inferencing. And it was able to generate 60,000 building footprints in 20 minutes. That's a rate of 3,000 footprints every minute. And you can imagine how tedious it would be for a human to do that. So let's look at some results. Now, as I said, this is a pixel classification model. So it doesn't just create polylines of these building footprints. For each pixel, it's predicting whether it's a building or not. And there are some flaws in this. As you can see, some pixels are wrong. And that's where the post-processing tools in ArcGIS, those geoprocessing tools, come in handy. And that includes tools to clean up the results, and this tool to regularize the building footprints that we've built just for this purpose. And when we turn on the regularized results, you can see how the model, how beautifully it has found all these buildings in a fully automated fashion. Now imagine a human labeling these meticulously, and we were able to get like 60,000 of these in a few minutes, except for the post-processing steps, which is also fully automated. So how many of you still think that it looks hard, but if I were to do it, it really, it's not that easy? Okay, not many are raising their hands, but I think there is some fear in some of you, which I'd like to demystify and show you all those steps. So here what I've done is I'm going to talk you through all the steps that are needed to train that model. So here we are looking at satellite imagery in ArcGIS Pro. And what we did was we were able to get some data from Chesapeake Conservancy from the Land Cover Data project. What they've done is that they've labeled each pixel as belonging to several classes. And we were able to get this land cover data for Delaware, for Kent County. And this is the Kent raster that we are looking at here. So as you can see, this has the land cover classes mapped out. Now what I could do is export the training data for this area of interest. So if I zoom to this layer, and since I want to do it quickly, I can call the export training data tool and run it over this area, basically by specifying that it should use the world imagery as an input raster and the Kent data as a classified raster, and given my area of extent, it should create classified tiles for that area. And if I were to go to that folder, and look at what it created, it has created these image chips that will be used to train our model. And here are these images, what they look like, several examples of the input raster. And using that, we can train our model. And I'll do that in this notebook here. So basically, let me just quickly run the cells while I explain it. We've imported the unit classifier from ArcGIS Learn, pointed it at the folder that we just exported, and here I'm visualizing what those image chips look like. So this has the land cover overlaid on top of the imagery, so buildings are showing as red. Now, we are creating a unit classifier, and here we are looking at the results of that model. So on the left is the ground truth, what it's going to learn, and on the right are the predictions. And as you can see, it's just garbage on the right. Model hasn't really learned anything because we haven't trained yet. So here's where we call the learning rate finder and use that to fit the model to our data for 5 training epochs. I'm only doing 5 because I want to do it live in front of you. And I'll use that time to explain what this learning rate finder is. Basically, what it does is that it starts with a very tiny learning rate, and the model keeps, this graph is showing the error rate. So as we train the model, the error keeps decreasing. That means the model is learning. And at some point, it'll stop learning and start shooting off in wrong directions. And that's when the graph starts going up. So you're supposed to pick a learning rate where it's still going down. And that's what I've done here. So it's still going down here at 1e-3. And that's what I've picked. And as right now I'm going through each of those training samples, the model is looking at that in each iteration. We'll do 5 of them. And we see how it's improving in accuracy and from 71% to 83% in just 2 epochs. And the loss or the error rate is going down. So let's see if it goes down further and the accuracy improves. Sometimes it goes here and there. It went worse, but we follow some best practices that uses a learning rate schedule that it first warms up, picks a larger learning rate that helps it generalize better, and then slowly ramps down. So over time, we should see with those 5 epochs, it should still learn something, and it would be quite obvious that it's starting to identify the major classes. So now we are at 87%, which is pretty good. And 1 more epoch, and we'll be done, and we can then look at the results. So right now, I'm training this model on my laptop. Nothing fancy, no supercomputer. It's very approachable. All of you can do it. All it needs is a GPU, which have become cheaper now thanks to the gaming people. So now we have a model with 87% accuracy. And if I were to rerun this cell here, we'll see the results of what the model has learned so far. Is it able to look at the satellite imagery and come up with the land cover classes? And now you can see how the model is not perfect, but at least for the major land cover classes, it started to know that there are some buildings here, there's some road here that's shown in the black pixels, and there are the 2 different kinds of green, which would be the turf and the forested areas. It found this road as well. So training a good model is all about giving more data to it and training for longer periods of time. And this is what I've done here. I've trained on the full data set of Kent County, and we get a model that's nearly perfect at finding these land cover classes. So now that we've trained our model, we have to do the inferencing. And we'll do that in this area where the imagery actually, you can see there's this row of houses here, but when this data set was prepared, apparently that wasn't there. So we see that this row of houses is missing there. And then it's just a matter of taking the the classify pixels using deep learning tool, giving it the model that you just trained, and running it over, in this case, just a small area of interest. And I had done that earlier. I'm going to quickly show you the results. And you can see, when I turn them on, how my model was able to predict these houses as being the right class as well. So that was semantic segmentation. It can also be used to do things like building footprint extraction. This is what we did for Los Angeles, and finding the different kinds of buildings. We saw an example of that. And a similar approach could be used to find roads. And this is an example from Redlands, where we used a UNet model, found these roads, and then used the post-processing tools to convert them into these line features. The next type of model is a feature classification model. You saw that in the plenary, where all the computer has to do is tell what type of object is in this image. And the example was whether the house is damaged or not. And we allow you to pick any standard deep learning model. There are models like VGG and ResNet, Inception. They're all part of PyTorch and Torch Vision. You can pick from any of these and easily train a feature classification model. The next type of problem is object detection. So given an image, you want to find what is in that image and create bounding boxes around that image. And we've got models like single shot detector and RetinaNet for that. So let me give you a quick example of that. So what I did here is I used a public data set of about 2,000 publicly known sites where surface-to-air missiles are launched from. This is what they typically look like. They're known as SAM sites. And this data set is public, and it's not the highest quality. And I used the publicly available imagery from the Living Atlas to export this data and train a SAM site detection model. So this is what those image chips look like. These contain several examples of what those surface-to-air missile sites look like. Using that, we use the single shot detector, which can find all objects in one image. And this is using the newer version of the learning rate finder. My previous notebooks did not show this red dot. Now it specifically tells you what learning rate you can use, which is optimum for you. Of course, as a data scientist, you can override it if you can interpret that graph. And by training that model, we started getting results like this, where it found these SAM sites. But some of these sites used to be SAM sites 10 years ago. Now there's nothing there. So it also learned some garbage. So what we got out of that model was these initial results. So if I were to zoom out and turn off the known SAM site locations, we got a lot of locations, but they had a lot of false positives shown in the blue color here. So we can do an iterative process and actually go through each location, and if it indeed is a SAM site, we can label it as such. And in the second step, I use this initial results to train a more sophisticated model, just like what we just saw, on all of that data. And here are the final detections, which are really good. So let me quickly show you some SAM sites that I found even as a novice non-image analyst. It's taking time to load. Let me try another area. Using public data and using low resolution imagery. So let me make sure my net is working. OK, Google is working, and it's replying. So
I'm working right now, if that's what you mean.
Google is working right now, if that's what I mean. Thank you, Google. So here are some results. And these are some SAM sites that the model found. And it's amazing that it was able to do that. And some of these sites really look like SAM sites to me. I'm not an imagery expert. And I was somewhat excited just looking at that yesterday night when I was creating these bookmarks. So another type of model that you can train is an instance segmentation model, which tells you these objects, but the precise boundary of each object, not just in terms of bounding boxes. And we actually use that to find these sinkholes that are cropping up near the Dead Sea. So what we did was we labeled some of these sinkholes. This is our training data shown in the black boxes here. This is what those sinkholes look like. They suddenly appear around the Dead Sea, and this is becoming a big problem because they can cause damage. So we use this as training data, and as you can see, it's not just bounding boxes that we had to label. We had to label the precise boundary of each of these sinkholes. And let's just go and look at some of the results. And we did that in the raster here. The area that we trained on was different from the area that we inferencing on. And as you can see, the model is doing a good job at finding where these sinkholes are. So just an example of using the same methodology, but a different kind of model. So how do you take this and scale it up? How do you do it for a whole country? Well, the same tools that you saw in ArcGIS Pro also work with ArcGIS Enterprise. And they support multiple GPUs. I showed you an example of that, of how we were able to scale this up for those building footprints. And here's a listing of those tools. And this is showing how you've got an ArcGIS Enterprise deployment on the cloud. This is your portal, and it's connected to your notebook server and a bank of distributed image servers on which the inferencing actually takes place. So depending on the volume of imagery that you want to process, you keep adding servers. And in our tests, as you keep adding servers, you can start getting results quickly. So in this example, for these building footprints, on one of our desktop machines with a one GPU, a GP100 GPU, it took 4.5 hours. But by scaling it up and using more recent GPUs, we were able to do that in 20 minutes for the 60,000 building footprints. So I'm sure you would have appreciated that no matter what kind of GIS problem you're trying to solve, whether it's finding the land cover or finding areas where there's impervious surfaces, there's a deep learning model for that. So here, for this, we would use a pixel classification model. If you just want to create bounding boxes around objects, you could use an object detection model. If you want the precise boundaries of each house, and even if the houses are jutting right next to each other, you don't want to just know which pixels belong to the house, but which pixels belong to which house. You would use an instance segmentation model like Mask RCNN. And if you were to simply do a categorization of features, whether it's damaged or not, or the swimming pool is clean, or it has algae in it, you could use an image classification model. And ArcGIS Python API has full support for all of these kinds of models. And we are adding more as we speak. And in addition to that, we also have support for text and natural language processing models. I showed you an example of that in the plenary, where we were able to take a bunch of police reports, label them, label what the crime was, when the crime occurred, any addresses in the report, and so on. We were able to take ArcGIS Learn and train a natural language processing model to extract these entities and plot them on a map on which we could do further analysis. So, how many of you like this? Okay, good. How many of you want to get started with this? Good. So I'm very encouraged, and what I showed you is actually in release software, and we have a lot of documentation and sample notebooks to help you get started. And here are some resources with which you can learn more about it and actually use it. And if you want to go beyond, you want to not just be at the surface, but really understand what's going on under the hood, I would recommend the Fast AI course, which is really good and lets you do that. So with that, I am done, and